So today, yesterday we covered strong normalization for the simply typed lambda calculus. And I mentioned yesterday that I was that I was going to try to give you, one presentation of logical relations, the standard one yesterday. And today I'm going to switch to a slightly different way of essentially doing the same sort of proof. But specifically we'll cover type safety today. So I assume that everyone here has done a proof of type soundness or type safety for simply typed lambda calculus using progress and preservation? Yes? Yes? You better all have more hands. Oh, okay, right, of course. Sorry, I walked in late. Okay, so we're going to prove type safety today using logical relations. Turns out you can do that. Let's write down a statement of type safety. Someone want to help me out? Type safety, type soundness. By the way, simply typed lambda calculus from yesterday is up on the top board with the usual call by value, small step semantics. So we want to prove type safety. What is it that we want to, how do we state that? We want to show that if a term is well typed, let's say if a closed term E has type tau, then it reduces to a value. Okay, that's actually strong normalization. That's even stronger than what I want. And I say that because I'm going to add recursive types to this language later on in this lecture, and at that point we won't have termination. Yes? I don't. Yes, and this is precisely my point. In general, what type safety should mean, or what we mean when we say type safety. There's this well-known slogan: well-typed programs do not go wrong. Right? Another way of saying that is well-typed programs do not get stuck. We don't want to get stuck, right? Like where you have something like true being applied to a lambda or something like that, or true being quite false. That would be a stuck state, right? You can't, that can't produce anything. And it's not a value. Okay, so in general, and the point I'm trying to make is the way that most of you are trained these days, and even I was in some sense, is, we get to of type safety as literally being progress and preservation. It is not. Progress and preservation is one method of proving type safety. It's a very syntactic, operational sort of method of proving what we actually want. And what we actually want is this property. We want to say that if a program is well typed, and let's say it takes a number of steps, some number of steps, 0 or more, to some E prime, then at that point in time, either E prime is a value, or there exists another E double prime such that E prime can step to E double prime. That is what we mean by well-typed programs do not get stuck. Okay? Here's a well-typed program. You've been running it for a while, or maybe you haven't even taken any steps yet. This could be 0, right? But at this point in time, at any point in time, either you have already reached a value, or it is possible to take another step. Means you're not stuck. Okay? Yes?
The type of E prime or E prime?
No, we don't. See, we don't need to. This is all we need. This is the top level theorem that we're interested in proving when we prove type soundness. When we use the method of progress and preservation to prove type soundness, there we always look at only one step reduction. Right? So let's think about progress and preservation, right? Let's write it down then. Progress says that if E is well typed, then we can always take one step, right? Then there exists an E prime such that. By the way, anytime I start writing too small, just tell me immediately. Okay? All right. And preservation says. Oh, yes, sorry. Then either, I'll just write val E to mean this wordy thing about something is a value. Okay? All right. So then either E is a value,
or there exists an E prime such that you can step to E prime. Right? And preservation says that if E is well typed and E steps to E prime, then E prime has the same type, tau. Right? And the point is that in progress and preservation, since we're always looking at one step, we have to sort of maintain, preservation basically, right? We have to prove that after every step, the type is preserved. And using these two theorems, or lemmas, we prove the theorem that we're actually interested in, which is this one, right? So we say that we want to show that if some E is well typed and E reduces to E, E has stepped all the way to E prime. Now we want to show that either E prime is a value or there exists an E double prime, right? So what do? We first go and use our progress lemma a whole bunch of times, and that tells us, we first go and use our preservation lemma a whole bunch of times, right? And that tells us that our E prime that we've gotten to here has the type tau, right? And then we can use progress, and we know that either E prime is a value or there exists another one. Yes?
This is a star. Okay, not a plus, yeah. So yeah, sorry if it's too small. It's a star, so it's 0 or more steps. Any other questions? Okay, so
we make the point that we're going to prove type safety directly using logical relations. We will not be using progress and preservation. All right? And by the way, right now we're working in a very simple setting. We're just working with a simply typed lambda calculus. But as you develop richer languages with richer type systems, sometimes, one issue with progress and preservation is that after every single step, you have to be able to type check your program. You have to be able to type check running programs. And sometimes, in order to be able to type check the running programs, you have to build a lot more stuff into your type system. At the end of the day, we only care about type safety. And so, the type system that you need in order to type check surface programs, the programs that a programmer can write down in your language, that system could be much simpler, depending on your language, than the type system, the enriched type system that you need in order to type check intermediate terms. And you wouldn't need to type check intermediate terms if you weren't using progress and preservation to do your proof. I just want you to keep that sort of as a mental note in the back of your head, all right, for the future. All right, and we'll see a very, very simple instance of this when we get to mutable references in a couple of days. There's a distinction between the type system that you might need to write down to type check surface programs that a programmer can write down, and the type system that you need in order to type check running terms or intermediate terms. Okay, yeah?
I want the designers of the language to care about what they can say about intermediate programs during execution. So I want them to care about the complex type system that's attached, even if it's not shown to me as a use case.
The designers of the language or the program?
The designers of the language.
Of the language, yes, absolutely. So what I'm saying about the type system not needing to be so rich in order to type check terms, it's not that the work required to prove type safety just disappears. It just moves somewhere else. The complexity moves somewhere else. But it's just a technical point that you should keep in mind when in the future when you design more complicated type systems to do interesting things. Perhaps you can get away without doing that and instead use a method like logical relations to prove type safety. I've done the same thing. So it's just an alternative. It's not that you have to do that. And my point then is that you, the designer of the language, will still have to think about what's going on with the intermediate terms in order to prove type safety. It's just that you will be using a different method or different device to do that. Okay? Which may not be any easier, but...
Okay. All right. So we're going to prove type safety. All right. So here's how we're going to approach this. We're using logical relations, again, a unary logical relation to prove this. I'm going to set this up slightly differently. We're going to define a value interpretation of types. So what we're going to do is for every single type in our, basically by induction over the structure of types, for the types in our language, we are going to write down when when values of the language belong to that type. Okay? So we're sort of building a model of types and sets. So let's start by doing this for bool. So what are the values that belong to the type bool? Okay. All right. Let's do functions. Okay. So what are the values that belong to the function type, tau1 or tau2? Lambdas, okay. So since it's tau1 or tau2, I better have lambda x colon tau1 here, right, to match this tau1 and some expression. And when does an arbitrary lambda behave like a function of type tau1 or tau2 specifically? Okay, so a function is something that you apply, right? So we want to capture how we use it. We want to capture its behavior. So we say, okay, if you give me some argument, some value v, that behaves like an appropriate argument of type tau1, then if I take that v and substitute it into the body of the lambda, e, right, basically after beta reduction, this expression will behave like an expression of type tau2. Yeah. Yeah.
Ah, good point. Okay. This is because we are in a call by value setting. Okay. So ultimately, when you have a lambda in your hand, at some point when
The actual, you will be applying it to a value form. You will have already reduced your argument to a value. That's why. If we were doing this for a call by name, version of simply type lambda calculus, I would put for all e in e of tau1 here. Not just value? Okay, that's a very good point. Okay, so this is an expression right now, right? So I clearly can't just put v here. Fair enough? So I'm separating my definitions out so that I have to think about value forms separately from expression forms. And I think this leads to a nicer, more modular definition. So in particular, right now, I haven't told you what this is. So let's define this next. Was there another question, or can we wait? Okay. All right. Okay, so we're going to define the set E tau, all right, the set of expressions that behave like expressions of type tau. So when does an expression, an arbitrary expression E, right, this is an arbitrary type tau, when does an E behave like something of type tau? When it reduces to a value of type tau, exactly. So, sorry? Or when it loops, exactly. So I want to capture that looping phenomenon. So let's not insist that it evaluate to a value of type tau. We're going to say that if, so for all E prime such that E reduces in some number of steps, 0 or more, this is a star, to E prime, and that E prime is irreducible, I'll explain this notation in a second, then we want to make sure that the E prime is actually a value of type tau. Okay, so by irreducible here I mean any expression that is either a value or is stuck. So irreducible simply means that there does not, that the that E prime cannot take another step. So irreducible of any expression is irreducible if there does not exist an E prime such that you can step from E to E prime. That's all. Okay, so that means it could be a value or it could be a stuck expression. All right. So what I'm saying is that you can take a whole bunch of steps, but eventually when you get to an irreducible state, you better have a value in your hands of the right type. that behaves like a value of type tau. Okay? Yes?
Can you motivate why stars both on the step of type safety and both the step and the E? I mean, my natural intuition is we work in like the one-step world. So why are we in the many-step world? Is it weaker or stronger? Like.
Well, so type safety in general should be, it doesn't matter how many steps you've taken till now, you should now be able to take 7 more steps. That's why I'm starting. Okay? And here, I'm basically saying, take however many steps you need to take to get to an irreducible step. Irreducible state.
Okay.
When you can't take any more.
Yeah.
Okay. So, any other questions? Yeah.
I mean, I'm assuming that, so, I mean, we have irreducible and value as different predicates because we haven't proved that they're the same yet.
Precisely.
Okay.
Yes.
So basically, we are saying that any expression, we don't know that this expression is going to reduce to a value. Well, it's a simply type lambda calculus, so you could say that it will reduce to a value. Let's try an alternative definition. We could have defined E tau like this. Any expression E behaves like it has type tau if there exists a V such that E reduces to V in some number of steps, and V belongs to V of tau. What is this definition doing? If we go with this definition, then we're saying that for an expression to, for us to say that an expression behaves like it has type tau, it must reduce to a value, and the value behaves like it has type tau. Exactly. Right. So if you swapped in this definition instead of this one, it would essentially be proving strong normalization, which is what we did yesterday, right? I was telling you that we were going to work with an alternative way of writing down the logical relation that, from yesterday in some sense.
I will add that. I just don't want to add it right now. Okay? I will add it in the second half.
Okay. So we're not going to do strong normalization. I just want to show you type safety. Okay. So now we have. So by the way, here I'm assuming that the values that I'm putting in here, we're building these value interpretations of types out of values that have this type. So syntactically, they're closed values. Right? So in a sense, whenever I have V tau and it contains certain values, I want it to be the case because the value has that type tau and it's closed. Whenever I write E tau, I want to put here I want to put an expression that is a closed expression that of type tau. Okay? Yes?
Can you recover preservation from this?
Recover the strict statement of preservation from this?
Yeah. So could you design a system that sets to some n-type values but then ends up in a y-type value configuration?
So somewhere in the middle, at an intermediate state. My first reaction is to say that why do you want preservation? You just want type safety. But I'm not sure.
Because you see here where we go all the way to an irreducible state. We don't even talk about the ones in the middle. Right? So at least with this definition, I don't think so. Okay? Or maybe you can. I've never tried it. I would need to stare at it before I say yes or no. Yep?
Irreducible. So irreducible right now could. Okay. So what does this definition say? It says that we get to an irreducible state, which may be a value, or it may be a substate.
Then we say it must be a value. Right? So, I mean, you could sort of say, why didn't I just write V here? Well, because basically I'm trying to build a logical relation with which I can prove type safety. Okay? So what I'm trying to prove is that you take a bunch of steps and you get somewhere where you can't take any more, and then I will show you that this is, in fact, a value state that you've reached. It's not an arbitrary stuck state. Yes? Yeah.
Yes.
And what is x? X is a variable.
Where? X is over here?
Yeah, so x is a variable.
X is a variable, exactly.
What is it? Is it a value or an expression?
X is just, well, it's an expression. But right now we're not, right now we're just dealing, it's not a closed value, right?
What is it?
X is not a closed value, right? What is it then? It's just a variable, so it's a form of, it's an expression of our language.
And since E is like the bigger thing, why don't we write in the second line, so for the lambda, why don't we write it at the end, an element of E? Why don't we write it like, I still don't get that.
Oh, why didn't we write B here?
No, this is applied to the calcium.
Ah, okay, so you're saying why not just do this?
Yeah.
Because that doesn't tell me anything. Here's what I mean by that. So think of this as a you know, you're trying to write down the semantics of when expressions or values belong to certain types. When they behave like they have that type. They don't violate the assumption of what we mean when we say that something has a type. Okay? We're too used to writing down type systems and saying, oh, you know, this is what this is. But like, think about it semantically, right? When we write down that some expression, if we can use the types, the typing rules of our language.
That E has type tau. What does that really tell us? In a semantic or operational sense. What does that tell us about what will happen when we run that expression? That's the question I'm trying to answer. Precisely. Yes. Okay. So I'm trying to say that, so what I'm trying to say here is that a lambda term behaves like it has type tau 1 arrow tau 2 if, when I give it a value that behaves like it has type tau 1, I get back an expression after beta reduction that behaves like an expression of type tau 2. Behaves like is kind of key here. By behaves like, I mean when you run it, it doesn't violate the assumptions that you have in your head about how this thing is supposed to behave. Okay? All right. So this is my way of saying that this is an expression that behaves like it has type tau 2. And then we've explained what we mean by that. An expression behaves like it has type tau if, when you run it, eventually when it gets to an irreducible state and you can't run anymore, you have in your hands a value that behaves like it has type tau. So it's kind of circular in some sense, right? Because now we go back to the value definition, but yeah, Michael.
This is on par with the SN form we used yesterday. It's just defining what we're attempting to prove. We haven't actually got to the mechanism of how we're going to prove that.
On par meaning? It is analogous.
Yes.
These are our logical relations like SN was our logical.
Precisely. These are logical relations like SN was our logical relation. In particular, when yesterday we were writing SN tau E, this is the equivalent of that, right? E belongs to E tau. I should say, E belongs to E tau is exactly analogous to writing SN tau. Okay?
Okay. Now, so far we've been working with closed values and closed terms. All right, so next let's talk about, just like we did yesterday, we needed to lift the notion of strong normalization, right? We first defined when closed expressions belonged to the relation Fn, and then we talked about lifting that notion to open terms. All right, so we're going to do an analogous thing here. Basically what I want to do is, I want to define a semantic notion. So here, type safety judgment. E has type tau under gamma, right? I want to define an analogous semantic notion, which I'm going to write with a double turnstile here, all right? And I want you to read this as E is an open term, okay? And it behaves like, when given, so again, going back to the slogan from yesterday, right? Logical relations, the slogan is that if you give me terms or inputs that have a certain property, then I will give you back outputs that have that property, all right? Or if you give me related inputs, I will give you related outputs. Okay, so we're going to try to define the semantic notion of safety, of type safety. Okay, so here's what I want to do. First, let's talk about substitutions. Again, substitutions gamma, just like we had yesterday. We're going to define a set G gamma, okay, of substitutions gamma. This is going to start to look very familiar, such that, by the way, little gamma, just like yesterday, maps variables to values. We want the domains of the two gammas to be equal, like yesterday. And for all x in the domain of gamma, it better be the case that gamma x, the values that these variables map to, belong to the value interpretation, sorry, not of tau, of gamma x. Okay? So I'm trying to say, what are all the substitutions that satisfy this type environment? These substitutions map variables to values. The type environment maps variables to types. Okay, so we basically want to make sure that we have mappings for exactly the same variables in the substitution as we do in the environment. And then we want to say that each one of the values that we have in our substitution behaves like a value of the right type, the type that gamma says it should have, that big gamma says it should have, right? Okay? And now using that, we can define our notion of semantic type safety, if you will, which goes like this. Basically, we want to say that for all substitutions gamma that behave appropriately, like, given a substitution that contains values of the right types, it should be the case that if we use gamma to close E, then we get an expression that behaves like it has type tau. Does that make sense? Questions? Yes?
Just quickly, our expression for closed expression.
Our expression relation is for closed expression, exactly. So here we were talking about closed expression, closed values of closed expression. So this is the expression relation, closed expressions here, and now we're looking at closed expressions. Any other questions? Okay. All right, so now that we've
This, I claim that in order to prove type safety, here's the theorem that I actually need to prove. Or it'll follow, but let's just say it this way. If E type checks under gamma and has type tau, then E will semantically behave like it has type tau under gamma. That's how you should read that. Okay. Now, before we go any further and even start to talk about how we prove this theorem, why is that the theorem that we want for type safety?
Well, we sort of push everything that our old definition of type safety had into at least the select part of it.
Okay. All right. And in particular, we can get once. So here's the really easy way of seeing it. Let's prove this corollary. Type safety, as stated over here, is simply a corollary once you have this theorem. So let's try to prove it. So we're going to try to prove this, given this. Okay? Everyone with me? Because once we have that, we know that this theorem is good enough to give us type safety. All right. So we are going to prove. Let me write corollary up there. This is the corollary we're going to prove. So let's see if this follows from this theorem. Okay? All right. So we want to show that. So here's the proof of my corollary. We say suppose, or we're given that E is a closed term of type tau, and we know that E takes a bunch of steps to get to E prime, and now we have to show that either E prime is a value, which I'm now writing as val E prime, or there exists an E double prime such that E prime steps to E double prime. That's what we have to show. Okay? Well, let's see. All right. We know that E has type tau. Therefore, let's go use this theorem. This theorem tells us that, from the theorem, we know that under a closed gamma, E semantically behaves like it has type tau. Right? Since E has type tau, E semantically has type tau. Good? Yes? Okay. So now we know that. Let's go look at the definition of this, of semantic type safety. Right? Okay. So E doesn't have any free variables. Right? Gamma's empty. Okay. So this definition tells us that you need to pick some substitutions, but we don't need to pick any substitutions because gamma's empty. All right. So this theorem then basically immediately tells us that gamma is empty. So E belongs to E of tau. Okay, so now, therefore, from this, we can, just looking at the definition, we know that to E of tau. Yeah? Okay. Let's go look at the definition of that. What does that tell us? That tells us that for all E prime such that E gets to E prime, if it's irreducible, etc. Okay, now let's make an observation before we do anything else. We know that here we're given that E takes some number of steps to get to E prime. Yes? Either that E prime is irreducible or it's not. Fair enough? Okay. So this E prime, it's either irreducible or not. Let's take the case where it's not irreducible. If it's not irreducible, then by definition it can take another step. Right? So we've just shown this. In the case where it's not irreducible, we can take another step. Good. We're done with the not irreducible case. Now let's consider the case where it is irreducible. All right? So now we're considering the case where E prime is irreducible. Okay. So now let's go look at this definition, because it tells us something about what happens when E prime is irreducible. So now we know that E belongs to E of tau, and we know that E has stepped to some E prime that is irreducible. Therefore, we know that that E prime belongs to V of tau. So therefore, E prime belongs to V of tau. By definition, that means that E prime is a value, and we're done. By the way, could everyone just close their laptops? I forgot to say this yesterday. I think you'll get a lot more out of it, unless you're using it to take notes or something. Hope this doesn't make me unpopular, but yeah.
Can you prove that? Statement, like the models of the field.
Completeness statement. Completeness makes more sense to me when you have a definition of contextual equivalence, so we'll get to that tomorrow. Here.
I want just the converse of the theorem that we have here.
That if E semantically has behaves like it has type tau, then it's type check?
Yes, that's my intention as well.
Yeah.
Sure.
What?
If true, then true, else true, plus or false.
I agree, I mean, okay.
Okay, sorry. So we see how Once we prove this theorem, we have type safety.
Definitions that we have on the board over here, they really have type safety just built in. Right? Okay. All right, so the main task then is, how do we prove this theorem? Right? Because we haven't really done anything yet. I've just shown you that if we could prove that, then we would have type safety. Okay, so let's push this up. And how would we prove that theorem? Induction on this typing derivation, right? Okay, so we have a bunch of cases. Again, let's do, it's going to bore you guys now, but just do it anyway. The case where we have true, just like we did yesterday. Okay, so now we want to show that true behaves like it has type bool semantically. All right? So let's just unwind the definitions. What happens? What do we have to do? We have to show this. Therefore, we say, suppose that we're given a gamma in G of gamma, right? We have to show that gamma applied to E, which in this case is true, behaves like an expression of type bool, right? Okay. Again, gamma applied to true is just true because true is closed, right? So this is equivalent to showing that true behaves like an expression of type bool. All right. So let's go look at what we need to do in order to show that E belongs to E of bool. All right. Looking at the definition, we have to show that for all E prime such that true steps to E prime if it's irreducible, etc. All right. So suppose true steps to some E prime that is irreducible, show